In exponential decay models, they're very similar to exponential growth. Well, whereas in exponential growth, something is growing exponentially, so it's being multiplied by the same percent each time. In exponential decay, well, it's decreasing by the same percent in each time period. So we have our exponential decay model right here. Y equals C times the quantity 1 minus R raised to the t. This is the only difference. There is a minus. C is still our initial amount, t is a time period, and this 1 minus R right here, that is the decay factor. Now, I did tell you about a different formula, a more generalized formula, and even for exponential decay it would be the same. We could say y equals a times b raised to the x. This b right here, remember that was our growth factor? Well, it also can be our decay factor. So if you're comfortable using this formula, you can think of it the same way. Just the reason we use 1 minus r or even 1 plus r is because we're dealing with percents. And so if we're increasing by percent, we're going to add it on to 1. That 1 represents 100% of our original amount. Or in a decay model, we're going to subtract it from 1. So we have 100% of our original amount, and we're going to subtract off a certain percentage each time. So both formulas, both models still work. Our initial value, our growth or decay factor, and then in this case our time period. So let's look at an example. It says from 1982 through 1997, the purchasing power of a dollar decreased by about 3.5% per year. Using 1982 as a base for comparison, what was the purchasing power of a dollar in 1997? If you use our formula of our initial amount times our decay factor raised to our time period, what we can say is our initial amount. Now, at first glance, it doesn't look like we're given an initial amount. But right here, we're talking about the purchasing power of a dollar. How much is a dollar worth? Excuse me, how much is a dollar worth? Well, 1. Now, to figure out our decay factor, we're going to go 1 minus our percentage. 3.5%, remember, is the same thing as 0.035. And then we're going to raise that to, well, let's just keep it as a t right now. If we simplify this problem, if we go 1 minus 0.035, that becomes 0.965 raised to the t. Now, remember we were supposed to multiply that by 1, but that 1 isn't going to change anything. So this is our model we can use to figure out the value of our dollar after so many years. So it wants to know what the purchasing power of the dollar was in 1997, and it says using 1982 as a base. So how many years after 1982 was 1997? 15. I hope you understand. So we can just type this into our calculator, and we're going to raise this to the 15th. So if you type that into your calculator, you're going to see that in 1997, compared to 1982, our dollar only had a purchasing power of about 59 cents. A dollar's value in 82 was $1. In 97, it was only 59 cents. Now I want to point something else out here. Again, we could have used our generic formula. Okay, our initial value still would have been 1. Our growth factor, our decay factor, would still be 0.965. Okay, and we still can raise this to the 15th. Understand when it's decreasing, we're going to subtract it from 1, or subtract it from 100%. If it's increasing, that's when we add it. The difference between the difference between exponential decay and exponential growth is in this growth factor. Let's go back to our original model here. Here's how you know whether you have growth or decay. It's all based on this figure right here, on your growth factor or decay factor. If it is a number, if 1, I'm just going to call this, well, let me use the other formula here. Y equals AB to the x. If B is greater than 1, it's growth. If B is between 0 and 1, we're not going to deal with negatives, then it's going to be decay. So basically you look at two things. This part right here, if it's greater than 1, because you remember from the other video, if it's 1, we're just going to have a horizontal line because multiplying by 1 isn't going to change anything. So if it's greater than 1, we have exponential growth. If it's between 0 and 1, then we're going to have exponential decay. Okay. Same formula for decay as it was for growth, but what's happening is our growth or decay factor, our rate, is going to be a number between 0 and 1 instead of a number greater than 1.